Hello, everyone. My name is Shranton Sen, and I'm here on behalf of the University of Texas at Arlington Robotic Vision Lab and the USDA Research Agricultural Service. Our work is titled Simulation-Based Multi-Fillet Evaluation of Woody Breast Poultry Fillets. I will go over what woody breast is in chicken fillets and why it matters. Then I'll look at the current detection methods for woody breast and its limitations. I'll go over the synthetic data and simulation framework and then end with our results and conclusions. Woody breast is a muscle myopathy where the meat becomes abnormally hard and rigid. The problem with woody breast is that it's hard to detect by just looking at it, so you have to use your hands and feel the meat or cut into it and look at its internal structure. Woody breast causes consumer dissatisfaction because of its tough and chewy texture, even after proper cooking. So when a fillet has woody breast, industrial processors have to divert it away from the premium whole fillet products into a lower value processing line. And usually trained workers are doing this manual job um, of determining if a fillet is woody or not. This whole process costs the US poultry industry around 200 million annually. So what the industry needs is a rapid, non-destructive way to identify woody breast chicken fillets from normal chicken fillets. So the current state of the art for automatically separating woody breast from normal fillets is by Yoon et al. They look at how the fillets bends under gravity as they fall off a conveyor belt. So a normal flexible fillet droops and bends under gravity while a rigid fillet stays comparatively straight. They use a side view camera at the roller drop-off of the conveyor and capture that bending profile of the fillet. And they reported a classification accuracy of over 95% in separating woody and normal fillets successfully. So the limitation with this framework is that it can only see one fillet at a time since it's looking at a single line of fillets. But a processing line is wide and has many lanes side by side of multiple fillets. So our objective for this project was to adapt this bending-based principle to a top-down view camera, looking at the whole fillet conveyor belt. Sorry, the whole conveyor belt. So why a digital twin? So to develop and test a top-down algorithm, we can't really experiment directly on a commercial processing line since that's very physically challenging and also economically challenging. So instead, we build a digital twin of a industrial conveyor system where we control everything and know the whole ground truth. The second problem is data. Chicken fillets vary a lot in shape, and there's no large 3D data sets of chicken fillet models. So a woody breast classifier validated on a small set of real fillets would not really generalize well in a processing line. So that's why our second contribution is also a synthetic chicken fillet data set. We started by scanning 40 unique real chicken fillets with a RGBD camera, which gave us 3D dense 3D point clouds. But 40 scans is not enough for robust validation. So our solution was to use few-shot transfer learning with a GAN. To make the generation easier, we converted the 3D point clouds into 2D depth maps, where the pixel intensities of the depth map represents the surface height of the fillet. These depth maps are what we fed into StyleGAN2. We took a model pre-trained on the Elchson Church's dataset and then fine-tuned it with our own data, which was the depth maps. The challenge here is that the standard transfer learning across two different domains, going from church buildings to poultry, usually causes mode collapse. So to prevent this, we used an algorithm called smoothness similarity regularization. So instead of forcing the new generator to structurally match the pre-trained one, SSR only transforms the smoothness of its latent space. So the loss here matches the gradients of both the target and the source generators. So as you move through the latent space, the generated fillets deform continuously instead of jumping between few memorized shapes. We also added an auxiliary 1x1 discriminator heads at every resolution to keep the global shape consistent without overfitting to our 40 samples. So we validated the synthetic dataset in two ways. First, with the kernel inception distance, which measures how well the synthetic distribution matches the real one. We got a low score of 0.081, so the synthetic fillets closely match our real data set. Second measurement we used was LPIPS. The synthetic set scores 0.289 versus 0.305 for the real fillets. So this is about a 95% of the geometric variation being retained from the real data. So that means that the model has avoided the mode collapse and has pretty much kept the same diversity as the original set. So we also did a nearest neighbor analysis, which confirmed that the GAN generates novel fillets and that it does not lead to mode collapse. So the simulation, our simulation is built in the Unity high definition render pipeline with NVIDIA PhysicsX for the physics engine. The conveyor belt runs at commercial line speeds of 100 to 130 feet per minute. We place two cameras, a side view camera at the roller drop-off, which we use to benchmark against the traditional system, and a top-down RGBD camera above the drop-off that monitors the fillet deformation across multiple lanes. We model each fillet as a chain of rigid segments connected by torsional springs. So each segment follows this rotational equation of motion with a inertial term, a dampening term, a stiffness variable, and the gravitational torque. We made each segment's mass proportional to its local cross-sectional area from the voxel volume, which gives us a realistic center of gravity shift as the fillet travels across the belt. And the stiffness K value is our woody breast severity parameter. When K is close to 0, the chain is very compliant, resembling a normal fillet, and when K is increased, it resembles a woody stiff fillet. So I mentioned before that we use two cameras, although one of our main innovations is using the top-down camera. We wanted to compare the results from a simulated side view camera against real data from Yoon et al. For the side view, we measure two metrics similar to theirs. The first one is the distance measure. That includes the minimum distance measure and the normalized minimum distance measure. For every frame, we segment the fillet's contour, compute its centroid, and then measure the distance from the centroid to the fixed roller or axle point. A rigid woody fillet projects further out into space, so it has a large distance, while a normal fillet drapes down near the axle, so it has a small distance. We then normalize these distances by the roller radius plus the fillet height, so the measure becomes invariant to the size of the fillet. The second metric we use is bending energy, which basically looks at the total structure deformation of the fillet as it bends. So this metric basically goes in the opposite direction of the distance measure, so a high bending energy would mean that that the tissue is very compliant, while rigid tissue stays pretty straight and has a low bending energy. So here is a demonstration of the side view camera in the simulation. The video shows a normal, moderate, and severe woody breast fillet falling off the roller side by side, and their distance measures and bending energy calculations at the top. So for the top-down view, the first task is to detect and track every fillet across the lanes. We do this but with depth-based background subtraction on the RGBD stream. And then we segment the fillets, which separates them when they're close together. So each fillet is tracked frame to frame by minimizing the centroid distance from each previous frame. We also do dynamic tail amputation, which means we cut off the front end of that fillet because the front end of the fillet can flop around a lot and moves around a lot, and so that adds noise. So we cut it off whenever the width of it drops below 30% of the maximum body width of the whole fillet. We also spawn identical meshes of fillets in every lane so we can analyze the effect of the camera's perspective shift. So now that we localized the fillet, we wanted to see how the shape of the fillet changes as it bends over the roller. And if we could actually differentiate that between normal and woody fillets. So the measurement we used is the shape score phi, So before the roller, while the fillet is still flat, we record a reference contour, the aspect ratio, and the solidity, which is the contour area over the convex hull. So as the fillet crosses the roller, its top-down footprint deforms, and the phi score combines the structural distortion measured with the hue moments matching distance with the change in solidity. So a flexible normal fillet deforms a lot, so phi is high, and a rigid woody fillet holds its contour, so phi is low. So here's the same comparison from the top-down camera. The three panel shows the different severities of woody breast fillets. So before the experiments, we had to, or before doing the experiments, we had to calibrate the digital twin. So at 100 to 130 feet per minute, the roller transit of these fillets only lasts a fraction of a second, and with real life masses, there's very little downward torque in that simulation, so the fillets barely bend. So we treat the mass of each fillet as a tunable parameter and calibrate it against the um, biological data from Yoon et al. Their measured NMDM separation between normal and severe fillets is about 0.25, and at m equals 100 in our simulation, our separation between normal and woody fillets is around 0.263, which is pretty close to theirs. So we use m equals 100 with the stiffness parameter k from 0 to 100 for all of our future experiments. So this table validates the twin against the biological ground truth. The top rows are the physical drop test measurements on real fillets, and the bottom rows are the digital twin going through the stiffness values. And as you can see, all three metrics move in the right direction pretty monotonically. NMDM and MDM rise with the stiffness, and the bending energy falls, which tracks the physical trends from normal through severe woody breast. So the physics of the twin come pretty close to representing the real measurements. Here's the top-down shape scores across stiffness values and line speeds. The phi falls consistently as the stiffness increases, so it doesn't just flag woody breast, it treats the severity of the condition pretty well. At higher speeds of 130, the added momentum reduces the absolute deformation, but the separation still stays pretty distinct. At 100 feet per minute, a normal fillet scores about 19, and a severe fillet at about 5, which is a 3.5x difference. Pretty substantial. And here you can see the differences visually. The normal fillet is on the left with k equals 0, and the severe woody fillet is on the right at k equals 100. Since one overhead camera spans multiple lanes, the fillets in the outer lanes are viewed at oblique angles. So we checked whether that affects the score. The center lane captures the widest range with a delta phi of 14.2, and the outer lanes only compress that marginally to around 13.5. And even in the worst cases, the lowest normal mean, about 19, is still over 3x the highest woody breast mean. So to summarize our contributions, we built a high-fidelity digital twin of an industrial conveyor with deformable fillet models. We also released a public dataset of our 1,000 3D fillet meshes along with the simulation source code. For future work, we plan to transition the top-down tracking system from the simulation to a physical real-world processing line, which will also involve real-world hardware calibration and some lighting optimization. That concludes my talk. Thank you for your attention.